How is it? Can you hear me? What about now? Nice. Okay. Mm, yeah, let's try again. Cool. So the idea of this um, is it better now? Mm, oh, nice. Mhm. Yeah, let me try. Okay. Um, yeah. So is there anything that you'd like to see specifically, or maybe we can discuss um, resume the documentation part also. I don't know how laggy it is or how delayed it is. It shouldn't be too much actually. Let me see. Yeah, I try to put as little latency as possible. Yeah, cool. So yeah, basically the idea here in this documentation or in this repo, the the main repo of HHAT is to at least right here is to define how the types will be designed inside the compiler. And yeah, the main idea is to have both classical and quantum types here. And yeah, there is the primitives, the struct, the enum, and the array. Those are the ways that you can represent a basically or define a type. Um, and yeah, where the magic where the things are basically structured Not this one. Mm, Core. Yeah. Yeah, it's basically we have this symbol ID that defines how you store data, like the tokens when you write a program in HHAT. Each token that have has some relevant information will be stored somewhere so they can be retrieved easily when the compilation process is running. And then basically they are stored in a kind of vector in Rust. So this symbol is basically going to start like the position in this vector. And this Boolean is basically to tell whether it's a quantum thing or not. So it really helps to verify things without having to like actually look for the data and uh, find it inside this vector. Because if you just possesses the symbol, you can just check for yourself. Um, yeah, and then yeah, there are some like primitive types, like the usual classical ones, and then the quantum ones. And the structure or the struct, like in Rust or C, where you have like the maybe it's nice to have an example here. Yeah. Um, I can have like type uh, something and then member one, type one, member two, type two, so on. You can also have quantum stuff. So yeah, member one, type one. You can also have um, quantum with classical. So yeah, and those basically are the ways that you can. So you have the names, which are basically the symbols, and you have basically a vector containing this member name and type pair in a tuple, which is basically this what we have. And yeah, just to give a general idea. Um, okay, explain the main reading. Um, let me see. No, yeah, this one. I think this one should be the actual README from the documentation, and this one is basically the README for the repo. So which one should I go to? Okay, so yeah, the main idea is to um, identify what HHAT is and yeah, to give some attributes or features that it's composed of. And basically what we have here is a regular description of a programming language, like you would have in other languages, such as Yeah, let me try to find an example. Um, yeah, I'll try something now. I hope it doesn't break. Um, oh, that's not it. Um, I don't know why it keeps happening. Like it zooms out everything out of the screen. Anyway, let me try make it bigger enough. Yeah. Um, so yeah, there are kind of some descriptions there regarding usually about the language and some features or some things. So maybe having something like that would really be nice for HChat. There are others that are more concise or smaller just to feature the main points. Um, but yeah, it's not like really clear that it's a programming language, so you should know that it's actually a programming language once you start reading. Um, Here as well, it's not like really clear. Then you need to kind of read a little bit more to understand. Oh, this is a actual programming language. Um, Python is, I think, the most generic one, um, but it's nice anyways because it's simple. Everyone kind of knows about Python, so probably that's the reason. Um, so yeah, probably there must be some kind of way to actually derive those informations without actually, I don't know, having to tackle all the issues about the specifics of the language itself. Um, yeah, I think that, well, I really like the simplicity of Go, but I also think it's nice to have some kind of descriptions because when the language is being built and things are different, so people might get confused on how they actually use it or what it is it for, and then they might not get some useful insights. I don't know. Um, But yeah, what else we have? Um, do you know any interesting like languages that have some nice descriptions? I don't even know if you can actually download C, so I don't think it has a website. Yeah, that's a very important question, maybe. Yeah, I mean, you don't even have a C language. Or do you? Really? Hmm, okay. That's new for me. Yeah, that's very interesting. Okay, yeah, Fortran maybe. Uh, yeah, yeah, that's also nice. There is kind of a basically a small sentence, then the features, very yeah, easy and concrete, and yeah, that's also nice. Yeah, C is also, but yeah, I don't think you can actually say much about C. It's just this sentence, and yeah, there's not much here. Um, but yeah, I think that basically yeah, we may have to define like what to see, or what we want to see in the language in the end. But Penny Lane is just a SDK, it's not a actual programming language. I don't think you can compare both. You understand what I mean? Oh yeah, but I mean, we are kind of looking to how to describe the language, right? Like there's not really information here. Of course, the documentation is good because there are many people working on that, and the language is, or the SDK is mature enough. But I mean, the presentation, it's yeah, it's like this. Yeah, doesn't say much. Is very open. The same with Qiskit, I think. Uh, yeah, so there is this information. Uh, yeah, to me this is strange, because it doesn't say Python anywhere, and then it just say install pip install Qiskit, and yeah, someone with no idea what pip install does might not get what to do. It might try to do that, and it will install Qiskit in the like systems Python. Yeah, probably it's not very good idea, but yeah. maybe it's just I don't know, but I think you know as Saad mentioned, clarity with the language, like the description. I think it's important. Um, but yeah, mm, so maybe we can redefine this sentence here and then try to do something like regarding um, how to say that it's a language in this is a project in under development and is you can have contributing with it. Take a look at um, the issues, maybe. Yeah. Hi. Oh, yeah. Thank you for coming, Azri. Uh, yeah. So we were discussing like how to have a better README page so people get more motivated to help to contribute or to do something with the language. Um, yeah, but do you think that um, we, sh we should have something like that? Yeah, so I can give some ideas regarding the project. Initially, it was built in Python. You can take a look at the repo right now. It's that there are kind of a few folders there, like the docs and the Python and the Rust folders. Originally, it was designed to be made in Python because I thought that more people would be interested in collaborating. But then I realized that most people want to start using it and they were asking like, yeah, what is it good for or when or how can I use it? So yeah, I realized that few people with Python knowledge would actually be able to contribute on the compilation side. And then I started, and the plan was first Python, and then people get to contribute, and then when things get more mature, we like translate that into Rust. But yeah, once I realized people were more interested into actually the Rust side or into the language side, not the actual language building side. Then I decided to scrap Python and go straight to Rust. Um, and right now it's kind of going from like the very internals of the compiler. Basically, maybe I can show here. So you have the H hat core and the H hat dialects, and basically the core is where you can actually have all the important parts of H hat that will be part of any development cycle in the future. And the H hat dialects are basically ways to produce different flavors of H hat for specific purposes. They can be purely syntactic flavors. Um, because one of the points that I always got was like when I showed the H hat in the early stage for people, they were like asking, yeah, but why doesn't it look like Python, or why doesn't it look like C or JavaScript or whatever their favorite language? And I was like, yeah, but if I write like this language, other people will ask about why it doesn't look like their favorite language. So I was in these like infinite discussions to try to convince people that yeah, the syntax is less important than the actual results. But anyways, then I decided to do dialects. So in the future would be possible to actually produce like a different um, syntax, but using the same structures that the other dialects use. Um, but yeah, so I just decided to do a very basic dialect to prove the concepts and do stuff. So going under um, the most critical and important part, I think it's regarding the compiler. So as you asked it, Osiris, uh, I'm not building from scratch. I tried, but yeah, it wasn't. Um, I mean, for a project that needs to show its um, what it's worth, I don't think it's um, reasonable to write everything from scratch. So, and because I don't like to write C++ code, I was kind of in a few options. One of those options was actually a very interesting one that I really like to highlight um, right here. So, of course, one of them is Trainlift, which is a very cool project. Um, so basically, it's used by the WebAssembly, yeah, Wasm-Time virtual machine. Um, so far, I've been liking it. It's kind of similar to some ways that the LLVM tries to achieve some things, but way, way simpler and less bloated. Another another tool that I want to try in the future is Plyron or Plyron, which is very cool also. And yeah, it's very interesting MLIR replacement or alternative through pure Rust, which I liked. Although you need to do some like compilations for LLVM stuff under the hood. Uh, so I'm still trying to understand how to avoid my infinite pain of dealing with C++ at some point. But yeah, that's why for now I'm just sticking with everything that CraneLift can provide, and yeah. So basically the idea, maybe I can show you. What? I hope you like drawings. So for the language, we have the parser, and then it will produce a kind of something that will go and to the compilation step one. So usually this step, it happens and you produce an AST. But I realized that we didn't gain much, so I decided just go straight to IR. Um, so far, I've seen that it's working very nice. So I basically call this HIR because it's a high intermediate representation. And after that, we have another step that goes to the compilation step two. So yeah, initially you have like, uh, yeah, the first thing that you have is actually the raw code, right? The source code, raw text. Um, so here we have the MIR that, yeah, it's the difference is basically that we on the HIR you have the like the most important parts defined as this data that is going to be verified. So you need to check whether the type exists, whether the function that it's being called was imported, and if that imported file exists, and if there is that function. So all these like very basic checks happens during this process of raw text to HIR. And then on the compilation step one, basically you are already like consolidating these parts. You need to actually transform those into more machine-like instructions or structures. So when we have the, for instance, the CraneLift IR, which is Cliff, if I'm not mistaken. So we need to transform to Cliff, and should be somewhere. Maybe I can find it here, documentation. Um, yeah, let me CraneLift IR. Yeah, so basically we need, yeah, it's a Cliff uh, somewhere, but yeah. So yeah, we need basically to transform like the HIR into a CraneLift, but for that we need to have like the HIR transformed into a way that it's easily convertible into that, because this is basically assembly like instructions. Yeah, there is a lexer. The lexer and the parser works together. Usually you kind of uh, simplify things and say, yeah, lexing, parsing are just one thing. But yeah, they must happen together, or not together, but usually they do. I mean, not at the same time, but you always consider them as a single thing, basically. And so yeah, what happens is we have HIR that is basically taking like the instructions. I'm trying to just give some ideas. We have some declare, uh, symbol v, um, type bool. So this is a kind of one instruction that is going to be inside the HIR. I don't know what is. Oh, yeah. So let's say, yeah, we are declaring this variable v of type boolean. So yeah, this is a instruction that is, let's say that in this step, the raw code, we would have something like this. So now on HIR, we are kind of having this structure that we have to declare the symbols, the types, and the action or the instructions itself themselves. And the MIR basically needs to convert this into something that is more convertible to this Cranilift style. And this happens like in this way. We would have like the declare, but now we would have like a symbol ID. Yeah, let's say 6, and we would have like a type layout for a single ID. Yeah, 64. So it means that we are kind of transforming things inside, and this type layout is basically a way to represent how the type is going to be addressed inside the memory. So because we have type layout of booleans, for instance, so it should be something like uh, a crane lift uh, type. I think it's E8 or something like that. So this is what we would have like as a layout for the type boolean. So it, I think it's types or layouts or something like that. But yeah, it basically has these informations like the type, the size. Oh yeah, it's the size, and you need to have the alignment. So yeah, usually it is this. Yeah, we can basically say it's uh, one because it's 1 byte, right? And the alignment is also one. And we can say we can also like represent it somehow. Maybe we can have a Cranilift representation, then it will be like that Cranilift types I8. So you kind of design how things will be because if you have a struct somewhere, it will get this information to design like the alignment and the size inside the memory and stuff like that. So yeah, this is kind of steps that are happening inside. And then the next part is basically the um, JT compiler and also the quantum program, which are the more interesting parts, I think. So basically you have here uh, Lift framework happening, and on this side you have like the quantum low level language happening. So it can be like OpenQuasm or NetQuasm or anything really. Yeah, maybe um, GeoIR, maybe Q-Sharp, etc. So the point is basically for the classical stuff, you are going to have this normal Craneleaf JIT compiler stuff that is going to produce like all these kind of instructions that will be executed in the computer. For the quantum program side, the quantum side will be transformed into whatever language, quantum low level language you have under the hood. And yeah, it will follow its kind of directives. So if you have a language that can support classical instructions, it will support it. If it cannot, it will fall back to the JIT compiler, basically. The main idea is that you, you always have some way to produce the code and not rely on like just breaking things because they do not exist on one side. Of course, the quantum side must exist in the quantum program, otherwise it will fail. But if the quantum low-level language does not have those classical instructions, they will fall back to Cranleaf. Mm, yeah, these yeah, that's a good question, Saad. Basically, I wouldn't. Some people may call it a like orchestrator. Some people may call it a manager. But honestly, for me, it's kind of the part of the compilation path. The idea is that you are going to know beforehand what instructions are available or not, because in the end you need to have like this compilation processing happening, all right? And you need to have a configuration, or you need to know which quantum devices you have. You need to know which classical devices you have. So everything is known at like before you even start compiling anything. And when you write your code and build it or execute it, it will be run like the compilation pipeline will run, but it already knows like what the things are runnable directly into the quantum um, program, or what are the things that should go to the JIT compiler. The only challenge is to communicate data between two. And for that, um, I've seen some, I've tested some ideas, and the most interesting ones are basically the ones from um, Erlang. So Erlang is very interesting language because it's made for like scalable, real time, and it's used for concurrency and distributed computation. So I think it has a lot of common goals to Quantum. And because of that, I thought, yeah, maybe learning about how it handles information, it's very valuable for HHAT. And I really like the concepts that it uses under the hood to handle like the information. So what happens is basically differently from HHAT, it has a virtual machine that will basically orchestrates everything at runtime. Um, because also Erlang is it has these kind of interpreted and also these just-in-time compilation parts. Um, so yeah, and it handles a lot of things that are not, at least not taught for HHAT right now. So I thought having a VM would be too overkill because you also Erlang is also kind of a soft operating system because it handles so many things under the hood, just as a operating system in the end. But yeah, regardless, I digress. The idea is that every single um piece of programming in Erlang is a process, and processes are kind of separated or encapsulated, so they are safe from the others. So if one process crashes, it doesn't affect the others. Yeah, thanks, Edward. Oh, Mattis, yeah, thanks. Uh, yeah, talk to you soon. So yeah, the idea is that you need to pass information from one process to the other, and there is this message passing protocol that Erlang uses, which is very cool. That basically you have some queues that receives and sends some data from one side or one place to the other. So it's like a mailbox. Some implementations literally call them mailboxes, which is very interesting. So basically, let's say that whenever one process is waiting for something, uh, it it just like stays in this open waiting uh, state, and then you can start as you put it aside, so you put it into idle state, and you can start running another process. And then let's say that you are running a process that will send a message to the first one. That means that once this process finishes, it will send a message to this mailbox. And then because it finished, basically the compiler or the VM will change its state to finished. So it will finalize the state and resume the idle processes. And it goes back to the process. And then the mailbox is checked and saw like, yeah, I'm waiting for a message. There is a message for me, so I can take that message. Yeah, so in simple terms, you have like this VM handling memory, but the memories are kind of not shared. So they need to go through this structure like the mailbox. to go through one side to one place to the other. So this makes the process more concise and safe for from crashes and things like that. Um, yeah, Osiris, I'm waiting for contributions for sure. Actually, there are some issues open. I'm going to open more issues soon because there are things that I need to include to make things more clear. As I was discussing with Saad, um, there are things that I'd like to have more help, and then yeah, I think everyone will benefit from it basically because I can try to offload some things and also teaching some concepts that are important for the language and like compilation and maybe Rust or maybe quantum computing. So whenever I can help out something and people can also contribute and teach me and teach others, it's very welcome. But also, we are participating the Unitary Foundation Unitary Hack. I always forget yeah, this one. Yeah, so we are basically available there. The Unitary Hack will start in June 3rd. So there will be a bunch of bounties that you can actually um, have if you want to contribute like for some things. I think it's worth. Um, yeah, it's pretty cool. You can participate in like all these projects. There are some. Yeah, I think they have some policies and rules and things like that. But usually you can keep, I think, up to four PRs open at one time. But yeah, you can contribute to uh, as many projects as you want, and there are plenty of them. So it's very cool. Um, yeah, so I don't know about, yeah, the bounties will vary. There are some values that they can provide, but yeah, usually you can get some nice bounties here and there. Um, yeah, so I don't know if I answer your question regarding how things are transferred from one side to the other. Because yeah, there's another challenge because here right now we are just saying that this um let me do this. We are just assuming that this is a single computer. So it's a uh, standalone local computer or local environment. Right? But there are times that there will be some distributed computation or there will be some concurrent computation across different devices, quantum, classical, throughout the internet. So yeah, there is also a way to actually send and receive those messages because in the end they are just like message passing protocol uh, data. Um, in hybrid algorithms, yeah, you may have that. That is normal. That is expected. Exactly. They are always like in order. because they have some indexes to keep the track of when you have to execute one thing and when you need to wait for the other. So that's the beauty on when you have like these message passing protocols. Because let's say that we have uh, yeah, that's a good discussion actually. You have a content instruction here, and you have a class construction, and you have a content instruction, and so on. So what happens is basically, let me make it bigger. Yep. So those are the actual instructions that you have to be executed at one point. And what happens is on on the quantum side or the quantum program, you are going to have like the quantum instruction one, or you execute the first quantum instruction and you execute the second quantum instruction. And then you have to like um, wait see instruction three. So when that happens, basically the HHAT compiler or the runtime will place this program. We can call this like a program or a process. Yep. So you have this process. We can make it smaller. Yep. And you may have another process that is basically the class call instruction. So you are going to have um, like wait instruction two and execute say instruction three and yeah, something else. So basically what we're going to have is like these um, things coming back and forth because in the end they communicate, right? And that's how basically the like network communication works. And literally it's how like the operating system works under the hood because it needs to kind of um, execute a little bit of a program, pauses it, puts in idle, resumes another program, and so on. Um, so yeah, that's kind of what we are reproducing here with HHAT compilation and runtime parts. No, it's not like, although you can also do that as a VM, on HHAT is pure compilation and runtime specific extra instructions. I didn't want to do like a VM because VM, it's a lot of complexity that you need to include in the code. And also, I don't want to get things bloated with a VM, a complete VM. I just wanted to have like these very specific concepts that we can introduce as small fingerprints or footprints in the code between like the instructions, the actual instructions, you know. So it's way more lightweight and easier to address things. Um, Dependency check for parallel execution. It's always sequential. The difference is that when something is waiting for the other, that thing waiting is put into idle. So the code literally stops there and something else starts running, which is basically how concurrency works. Uh, right now in your computer, um, yeah, maybe not in like current computers because they have many cores, but let's say that you have a one core computer. Usually you can run multiple programs at once because the OS is making them run a little bit at a time, but because it runs many times that per second, you have the illusion that things are running in parallel or at the same time, right? But the magic trick is that they are just running a little bit at a time, but the frequency is also high, so that's how you don't feel that they are kind of uh, slowing down or getting delayed or getting frozen. Uh, so yeah, that's how things will work. But this, yeah, indeed. There are things that would be possible to execute like at the same time for sure. Um, I just need to check whether it's worth doing it, implementing this feature in the ver in this version or not. The reason I say that is because you need to check whether the instruction that you are going to execute does not depend on anything prior. So you need to do extra checks to make sure that things are in the right order, in the right like place, and they do not affect other things. So depending on how complex the program is, you need to do some extra steps to ensure that. Um, but regardless, this is the like I would say the case where the actual quantum low-level language does not support the classical instruction. Because if it supports that specific instruction, it will just run inside the quantum program. And the quantum program is basically a way to represent the instructions that will be running to the device, right? So let's say that we may have OpenQuasm 2, or we may have OpenQuasm 3. And the difference between both is that OpenQuasm 2, it cannot run most of the classical instructions. But OpenQuasm 3, it can. And then it means that it will be able to run many of the classical instructions already in itself. So it's up to that language to handle all the classical instructions themselves. And if it turns out that there is still some instruction that it cannot run, then it falls back to the actual HHAT runtime part or compiler part. That's basically the idea. But yeah, what else? Maybe I can show some code uh, for this. Because yeah, I was mentioning about the compilation and so on. So what I was doing right now is basically I have defined the types as the like HIR uh, representation. So you have the type, you can say it's a primitive, a struct, and whatever. And you have like for each of them, you have some ways to represent things. And the second part, the like MIR, the MIR basically means that like the kind of middle intermediate representation. So it's between like a full or a almost descriptive language that is the HIR, that is a high intermediate representation, and a crane lift representation, which is a machine code representation. So yeah, the primitives basically have like some definitions. Like sometimes you may have, usually you can have like the single types, which is basically like the booleans, the integers, etc. But I decided to also have the complex numbers as also like primitive types, just like in Fortran. I think it's useful for quantum computing and probably for the quantum algorithms and classical algorithms and hybrid algorithms that people are going to use. Yeah, it's that's true. The MIR is like a instruction register, but it's even before, a little before that, because here we are kind of defining the layouts for the actual types that we defined in the type for the HIR. So in that sense, it's like we have the raw code or the raw text that is just plain programming language. Then we have the HIR that is basically transforming that into structured data, but it still has like some elements there that are still present in this in the syntax. The MIR is where you kind of abstract away those things and you are more interested into how a specific type is represented in terms of memory layout rather than saying that the type is called something, you know. So at this step, we are basically going to replace all the type representations into the actual type memory layouts whenever it's needed, just to prepare that for the conversion from the MIR to the Cranilift IR. So it's, yeah, usually it's a common practice. You can also see in Rust. Rust has some extra steps before and after, but also it does a lot of checks in between, not just like transforming the type layout. You also need to check whether and where the variables are properly initialized and dropped, whether you are not like um, reusing the same variable in multiple places at the same time, just like in Rust, because you need to have ownership with for, for it. So you can just use it once, or yeah, you can use once quantum data, but the more important part is you can use um, just once at one time, just like in Rust. So there are checks that are quite simple to do. That's why I decided to include them. Of course, there are no intricate ways to check like Rust does right now. I don't plan to do that in this first version. I just want to have the very basic things that ensures that the user is not doing things um, so wrong, but also yeah maybe some more intricate or complex cases it may not catch at first. But yeah, that's the language development. So I think that's totally fine. It's more important to move into things and then see where it needs more attention later when people start using it. Um, so you ask about the impact on the MIR, IR, and the orchestrator. You mean regarding the order of the instructions to be executed when you have like a quantum program or something like that? Because usually, um, of course, the idea is that each of these steps, they basically transform exactly the same code into something else that fits more to something, right? So why we get the raw text into the HIR, it's because we need to transform those tokens into something that um, the compiler can reason about, can check things, can start structuring things, and give names to things, and starts to organize the ideas and see whether things are well structured or not. Um, um, yeah, I mean, every single step is a step, right? So you need to check the whole code on every single step. The advantage of having like some intermediate steps in between is that you can shrink some code because yeah, you already know they work or they are sound in that step. And yeah, sometimes you can optimize some things in those steps, or you can improve the structure, and then it will be slimmer or smaller. So every time, every time that you go a step towards the machine code, you are kind of stripping away all those extra details that kind of makes the code readable for humans, but it's not useful for machines until you basically get into what we have in, for instance, let's say Rust. Rust has many steps. Um, it has AST, so basically it will transform from raw text into AST. It will do some checks. It will do maybe some small optimizations. And then from AST, it goes to the HIR. And then there it will do some checks. It will do some optimizations. And it will go to MIR. MIR, again, some checks, optimizations. It will lower to the LIR. And again, it will do some extra checks, extra checks, extra optimizations. Then it will convert into um, the standard Rust compiler. I think it's LLVM, but you can also have CraneLift because it's a side project that I saw that they are still trying to have Rust being compiled into Rust. uh, own ecosystem. Uh, but yeah, the idea is that for each step you have, you gain something when you do some checks. Sometimes you cannot do some checks in one step because you don't have enough information. So that basically means that you are going to do some iteration over the code that you generated again because now you have more information that you had before. One example is that let's say that you have a file that imports some code, some functions and types, and below it you have like the usual functions and instructions and things happening under the hood. So yeah, you can think of any language that does that, right? What happens is when the parser starts for the lexer and the parsing part, it will just convert like the string of strings into something that is tokenizable, right? And then you need to do that first step on all your code. Just after that, if everything is right according to the grammar that you defined, only after that you can do the next step that is actually transforming that into something more machine friendly. So the first step after that is to actually understand, okay, is the code structured properly? And if so, what I need to do next? So let's say, yeah, I need to import. So I need to check if that import is existent and if that function or type is there. So I need to go to another file, I need to open that, parse that, and do all over again. So this is kind of the process that you need to do, you know. So that's why you need like different IRs throughout the code. So this is to generate the AST or in our case the HIR. And after you verify those things, to transform the HIR to MIR, you basically check the memory layout of the types. You start basically placing uh, like the functions and all those instructions into ways that they can be transformed into machine code instructions later on for the crane lift IR and the assembly later. So yeah, it's not a bad thing and it does not like degrades the performance. Of course, if you do too many um, steps or too many checks when it's not relevant or needed, you are going to have performance issues. But then again, it's like it's a matter of understanding how to tackle that and how to improve that later. Because sometimes you just need to provide some code to see what works and what doesn't, and later you can improve and optimize that. Um, and yeah, also I was doing the struct layout because we need to have like the size and alignments for like the whole structure and for each member also. Um, I don't remember where I. Oh yeah, that's something interesting. Like um, yeah, let's say for the U32 or the I32, you have like the same size in bytes, the same alignment, and like or kind of the same crane lift representation. Representation in crane lift, it doesn't have like the unsigned 32 or any unsigned value, but it's then regarding to how the instructions will interpret this type basically. Some instructions are unsigned, so when you provide this signed one, it will convert to unsigned and vice versa. So yeah, as you can see, you have like the size and alignment. So this is important for like the enums and for the structs. But for the quantum side, basically you don't have any size and alignment because all the information will be carried out in the quantum program, and the quantum program has its own memory layout because it's related to quantum. And then it will have like the qubits memory layout and things like that. So this is a new, that's the new interesting part of this um, hybrid programming language in the end. I don't know if that's interesting or relevant, but yeah. Yeah, what else? Which is relevant here? Mm, yeah, for now, I'm not, yeah. Yeah, it's mostly in um, this branch, I'm mostly working on this layout stuff because I was missing that part for the quantum program logic. Um, so yeah, here also you can define like where in the memory region some data will be stored. Uh, yeah. Let's say sometimes you have the global scope when you have some constants. You may place things in the stack. Usually that's the usual way where you go if you have like compile time data. But yeah, some when not, you have to go through the heap memory. And one part that is relevant here, um, it's basically that, where is it? Type. Yep. So types. You can have the static types. That is basically what you have in arrays in Rust. But you can also have dynamic ones, which would be something like the vectors in Rust. So yeah, you can have both kind of arrays. So in that sense, the static one will be in the heap, dynamic one, or static one will be in the stack, dynamic one will be in the heap. And I think I put this somewhere. Oh yeah, here, the memory region, the default. So if the array is dynamic, then it will go to the heap. If not, everything else is kind of the stack, at least for now. And uh, yeah, you can also set the memory region if something is kind of must be changed. Let's say that you have a constant, so you can reset to like global region or global scope if needed. But yeah, by default, it's kind of this approach. Uh, and yeah, this part is where the MIR happens because it's more close on how to organize the data itself inside the memory. So this is not the work for a HIR. That's why I think it's relevant to have both because they have different roles. And because the roles are distinctive and very clear, it's easier to reason about them and see, oh, okay, I understood this or that. So But yeah, how is it going? Or maybe I can just finalize the string. I don't know. Um, any more questions or what else? Actually, um, which languages you are familiar with, Ozri? I can tell you that um, it took me a long time to start actually writing code in Rust because, yeah, I felt it was very difficult. The syntax is very difficult. Uh, oh, yeah, Verilog is very nice. But yeah, coming from Python, yeah, it's totally different. I think it's very different language. Um, one thing that really helped me to get into Rust, because I was like, I want to learn it, but it seems so difficult and too complex, like too many features, too many syntax sugars, too many things to think about, or yeah, they are just bloated in your face, you know. But I can give you an example. Uh, yeah, I'm just writing something nonsense just for you to understand. Once you get used to it, it's kind of easier. So you can decide if the type will be available for anything or just for this crate. So crate is basically a library. So if you put pub, it means that it will be available for everything. If you don't put it, it's just to be used locally in this file or like in this folder where this types is in. So let's say that I have a struct called A, and there are things that I can do with it. So those things you kind of need to memorize, but once you do it, it's kind of natural. So there is this thing called derive. So it means that you can provide some extra code without actually writing extra code. So if I say debug, what is going to happen under the hood is basically the Rust compiler will actually expand this struct and write for me something about this debug so I don't have to care about it. In practice, what does that mean? It means that, let's say I have um, some value here that is going to be Boolean. So I can implement debug for A, and then I need to implement the missing members. Yep. So it means that right now I need to implement this stuff. So I'm going to receive this F. So in theory, what I need to do is to have this uh, right that is going to receive this F and something else. Um, oh, it's the opposite. Yeah. So yeah. Mm, no? Oh, yeah. F, and then I need to I string from uh, oh, it's because it's right. Yeah. Yeah, that's kind of annoying, but you get used to it. So yeah, instead of writing like maybe I have the self and value here, then I will print the value and self here. Maybe I want to say, yeah, I want to have A and having it like that. I don't know if that works, maybe not. But yeah, let's say that I just want to have A and Boolean. So whenever I have like a println uh, something like A dot value or or even A, and the A is basically the A like if I define that A P um, value true, and then I have A here. So this is from this format from this debug is to actually implement a way to print out to be able to understand how it should print this struct A. But if you just want to simply like print the structure itself without anything extra that it's not relevant for you, you don't have to write everything by hand. You can just derive it. So the Rust compiler will figure out for you like how to convert this structure into a debuggable thing. And it can also do like implement a cloning thing. So if you want to be able to use like the a.clone to clone the data, it's implemented for you. If you want to check for equality, like assert equal a equal a, or I don't know, let's say that we have b that is also like this. So you can also do this comparison now. So yeah, there are some things that are overwhelming in the beginning, but you kind of get used to when you learn more about the language. But what really helped me to understand Rust was to learn Haskell and to learn Erlang. And they really opened my mind on how to understand and use Rust. So if you want to try Rust and it's overwhelming, like I felt, maybe trying some other functional programming languages will really help on that. I recommend Haskell because it has its very strong type system, which basically trains you to be like more aware of how to handle types and what they mean in terms of logic and construction of things. Uh, but what I can say is that once I learned it, I cannot use Python anymore. I use it Python a lot for many reasons, but Rust is so much more interesting to code, and the code itself is very pleasant to write. So yeah, I really enjoy doing stuff in Rust. And of course, it has its very strong format checker and analyzer. So you don't have to depend on external things to make the code run or to the code to work. Basically, everything comes together and they are already so good that you can just start programming and things will work. So yeah, that's what I really like. Besides the fact that it's compiled and very fast, like C like level of speed once it's compiled. And another thing that I really like is kind of you can basically use the option uh, or the results. So let's say that you have a function and let's say that you have two variables. Uh, mm, yeah, can be string. So what happens is basically, let's say that if A equals B, then yeah, I want to return okay, true. Else I want to return like an error. Uh, yeah, string from, yeah. So I think this is very powerful because now I don't have to handle like if, throw, error, everything's inside a type. So it's so much easier to handle that. And if I have another function that will do whatever, uh, and then I just need to check like that, or yeah, really just something true and false. Uh, I can even have this match directly, so it's very nice. I don't know why it's, uh, yeah. So I can have like, okay, result, and I can do something with it. Like, yeah, I can print the result. If it's an error, it's already a string, so I can just also do the text. Um, so yeah, it's very nice to program because it's very clear what is happening. There's no like exceptions like Python or JavaScript or other languages. I really like that. Everything is very clear and very easy to understand. The errors are actually part of the logic. So it's not something annoying. It's just something that happens and then you are prepared for that and you can just handle them whatever you need. So I think that's very neat. But yeah, I think that's interesting, but also that's kind of difficult to to learn from scratch. Um, yeah, if there's nothing else, yeah, I may want to close the live for now. It was just one first attempt, but I hope that it was interesting enough. So yeah, I can, if that's worth, I can make it like a weekly activity, like every Thursday. Yeah, no problem. So yeah, we see each other next week, and then yeah, if you have anything that you want to discuss, just drop by the Discord server and send a message on the chat. Sounds good. Thank you very much.